Hello, everyone. Thank you for having us at Fragile Earth. My name is Rebekah Loving, and this is Arushi Agarwal. We are both students at Caltech. Today, I will be talking about our work in aiding forest conservation. As a native Hawaiian, I feel very strongly about protecting the forests of Hawaii. And one of the things about the ecosystems in Hawaii is that they're very delicate, and the native plants have been really overrun by invasive species as well as different diseases. And so a lot of manual review is needed of aerial footage as well as in-person manual reserve inspection. And so we wanted to ask the question of whether or not we can improve on current computer vision methods to automate tree detection and classification on both seen and unseen species, and how this can be used also for looking at invasive and native species, as well as healthy and unhealthy plants. And we wanted to see if these methods can then be used in protecting forests in Hawaii. And so we'll talk about a network fusion model pipeline for multimodal deep learning tree crown delineation and classification. So past work in this area has been mostly using only RGB images and has really focused on deep neural networks for crown detection methods. And so one of the things about the NSF neon AOP data, which we will be using, is that there's 3 different modalities. There's LiDAR-based canopy height models, which is just taking the height of the canopy versus the ground. And then there's RGB data, which is what we're all familiar as images. And then there's hyperspectral image cubes, which is taking 369 different bands of spectra from over 380 nanometers to 2510 nanometers. And so we are going to use all of these different modalities of training data from the NEON data set. And one of the really premier models that has been applied to problems in detection, tree crown detection, is the deep forest model from Weinstein et al. In 2020. And this was used and pre-trained on millions of moderate quality LiDAR algorithm annotations, and then retrained on about 6,000 hand annotated RGB images. And in our work, we will only train on about 6,000 RGB images. And the predictions are made only with RGB data. And in our work, we'll use all 3 different modalities. Deep forest, however, did attain a precision of 0.61 and a recall of 0.69.
So before going into our architecture and approach, I wanted to go over some of the building blocks of the model first. So we have 3 different components of the model. One is the backbone, which is a baseline network, a modified version of the SSD300, which consists of a modified version of VGG16. In addition, we have auxiliary convolutional layers, and finally, we have a set of prediction convolutional layers. We use feature maps outputted from the baseline VGG16 network, pass those into the auxiliary convolutional layers, and then use feature maps from the auxiliary layers to run our final prediction layers. We also use a multi-box loss that consists of a localization component and a confidence component. So going more in depth into our prediction convolutions, we use a set of prior boxes that represent the probable box predictions for our bounding boxes. Using the outputs from the prediction convolutional layers, we can use the feature maps to find our predicted bounding boxes encoded as offsets of the prior boxes. In addition, we can use our prediction convolutions to extract class scores and threshold on those scores to extract only those bounding boxes that we are most confident about. So finally, going over our first approach, I want to first reiterate our goal. Can we improve detection performance with network fusion by incorporating feature maps from all 3 input modalities, RGB, CHM, and HSI? We have 3 stages to our network. One is to pass in RGB, CHM, and HSI to separate baseline networks, which are the VGG16 backbone architectures that I mentioned earlier. We use the outputted feature maps in our auxiliary convolutions after they have been concatenated and use the resulting feature maps to predict bounding boxes through the prediction convolutional layers. When we visualized the results from our first approach, we found that a lot of the unique data that we have in all three different data types, RGB, HSI, and CHM, were almost all disappeared by the time they passed through all of the convolutional layers. We looked at two different sets of maps from two different locations in the model, and we noticed that the feature maps did not have any meaningful input that was being passed on through the rest of the model. So it was not unsurprising that the bounding boxes that we predicted were not meaningful.
However, when we looked at the feature maps from when we trained on each of the modalities independently, and here we show the CHM and then the RGB, we saw that a lot more of the information of these different modalities was being retained. And so in the CHM on the top left, you can see that the canopy information, that height information is really being transmitted through the different feature maps and captured in different ways. And so that's really important to see. And then in the RGB images, you can see that the RGB information is being extracted out of that RGB image into the different feature maps in different ways. And so that was something that led us to think, maybe if we train the feature extractors separately, then we can actually capture more of the information and get better bounding boxes being predicted. And so when we did this approach, we decided to use a sequential feature extraction approach and then network fusion. And so the goal of this was looking at, can we improve detection performance by incorporating independent feature embeddings for each modality? And so we did this by first freezing HSI and CHM baseline backbone heads and training only the RGB head. And then we froze the RGB head after it was trained and trained only the HSI head, the backbone. And then we froze the HSI head after it was trained and trained only the CHM head. And then we froze all three input heads and we trained the auxiliary network. And when we did this, we achieved the following results.
So here is a set of visualizations for our predicted bounding boxes versus the ground truth bounding boxes for all three of our different data types, CHM, RGB, and HSI. As you can see here, a lot of our bounding boxes closely match the tree crowns in the image and are very similar to the ground truth hand annotated image that's visualized below, almost as if our predicted bounding boxes were annotated by a different person. Finally, we'd like to go over some quantitative results from our models. Here is a precision recall curve. First, we have this recall curve that represents our first approach, which was to use all three modalities, RGB, HSI, and CHM, with the features concatenated and passed in before we run the prediction convolutional layers. We also have three different precision recall curves for each input passed in individually, HSI only, RGB only, and CHM only. And I'd like to point out here that these three precision recall curves represent the set of classical approaches that are being used currently, where a single input modality is passed into the model and used to predict the bounding boxes. So already our first approach of combining all three input data types surpassed the classical approach in terms of both precision and recall achieved. Finally, this blue curve represents our second approach, which was the individual feature map fusion model, where we achieved a final precision of 0.4 and a final recall of 0.6.
So we are very excited by these results. by both the sequential training and the network fusion with multimodal inputs, producing improvement on the traditional approach. However, a really big what if still remains of whether or not the deep forest is actually better than our method, since, as you remember, the precision and recall were 0.69 and 0.61 for deep forest, and we did not achieve that as yet. And so one of our first goals for future work is to train our model on the millions of rough annotations first, and then use the hand annotations as deep forest did. One of the other things that we want to do is look at whether or not total independence of the feature extraction rather than sequential training improves the model performance as well. And then we really want to transfer learn this to the UH-Hilo data to see how we can actually use it in the Hawaii forest as we really would like to. And one of the things that we will be doing imminently is working more closely with ecologists to adapt our evaluation metrics to their needs and make our model perform better to actually impact the forests that we want to preserve. I'd like to thank and acknowledge all of those on our team, Arushi, and Ilya and Sarah, who put so much work into this. And I'd also like to thank Ben and Sarah and Elijah for all of their input along the way and helpful guidance, as well as Nihar and Pedro for supporting us. Thank you.
Thank you.